Okay, I think I can make this pretty quick. Crown ethers, metal atoms with a full or partial positive charge. This is interesting. Watch this. Metal atoms with a full or partial positive charge can be stabilized by ether solvents. All right, so we found out the ethers are relatively nonpolar. Well, they're relatively nonpolar compared to alcohols and waters, but because they've got this lone pair of electrons here, they can stabilize metals. And you know, metals are oftentimes cations, right? So sodium, lithium, potassium, right? These are all real common metals that we use, and ethers can help us with that. Okay, so ethers are generally used as the solvent in Grignard reagents. Remember this reaction from lesson, lesson 2? Right, making a Grignard reagent. Well, you can't have water in there because this R group acts like a base, right? Sorry. Okay, and that's because this metal, these electrons right here are almost entirely with the R, and that's what makes this such a good nucleophile. Okay, what's that? But that leaves behind this magnesium's got a plus on it, or a partial positive. Okay, so ethers are perfect solvents for Grignard reagents. Okay, give another reason why ethers make a good solvent in this reaction. One more reason. I've sort of implied it there, and I'm not going to tell you what it is. What's another reason why ethers make a good solvent in this reaction? Okay, so crown ethers have been shown to form especially strong attractions to metal atoms. Why? Why is that? Well, you've got all these, look at this. Can you see my lone pairs here? Are those too small? All these lone pairs, right? Look at that. Wow. All these lone pairs. Just a ton of them. You can see that. It's a shroud of lone pairs, right? And so you can have a big positive in here, and you've got all these negatives or partial negatives, right? Which blanket that. Beautiful. Okay. How many carbon atoms separate the oxygens? How many carbon atoms separate the oxygens? Why are they called crown ethers? Can you guess that? And then the next question, of course, is explain the numbers found in their names. These are good questions. I got these from Klein, by the way. I didn't write these myself. These are great questions. Thank you, David Klein, for giving us these questions. Look at them. Explain the numbers found in their names. 12 crown 4. Where's there a 12 in here? And where is there a 4? 15 crown 5. Explain those numbers. Okay, now, the size of the metal, of course, has got to match the size of the crown to form a good attraction. So can you see you've got carbon, carbon, oxygen, carbon. Can you see that from where you're sitting in that video? Make it okay? Carbon, oxygen, right? And the white balls are the hydrogens. Well, those are just the nuclei, right? The electrons really make more space, okay? So it turns out that 18 crown 6 fits a potassium atom. Wow, just right. Nice and snug. Okay, and that makes a crown ether, 18 crown 6, a good solvent for potassium ions, right? Okay, so normally metal ions are not soluble in low. This is another good question. Why are metal ions typically not soluble in low polarity solvents? That really should be obvious to you at this point. Now, if it's not obvious, it's probably just because of the jargon. But you've done these things successfully many times. The kind of thinking that you've got to answer that, you've done that. All right, so bend your mind on that. Why are metal ions not soluble in low polarity solvents? Okay, the crown ether metal complex should dissolve nicely in low polarity solvents. Why? Why is that? So you've got a low polarity solvent, which is maybe an ether, right, all around this guy, and it dissolves just fine. Why is that? Imagine how a crown ether could be used to aid reactions between ions, okay, especially anions. So you don't really have to imagine that. I've got a slide here for it, thanks to Klein. The fluoride ion below is ready to react because the potassium ion is sequestered by a crown ether. So if you take potassium fluoride and you put it in 18 crown 6 and then put those together in benzene, then what you've got is your potassium ion gets sequestered and your fluoride ion is ready to work. Okay? Without the crown ether, the solubility, so if you don't have this in there, potassium fluoride is not very soluble in benzene. Why? Because of polarity, right? Okay. Now the fluoride ion is not used as a nucleophile in general because it's strongly solvated by polar solvents. So it gets into polar solvents fine, but the polar you've got a fluoride ion which is really small, and it's dissolved in, how would it be? Let's say water, okay? It's blanketed by these water molecules. It can't get in as a nucleophile. It's like a nucleophile, right? It is a nucleophile, but it's like a nucleophile that's all covered up. So it's in a box and you can't get out, where the box is made of the solvent, right? In polar solvents, it's boxed up. Such solvation greatly reduces its nucleophilic strength because it's all blanketed, right? In the presence of a crown ether, however, it's soluble enough in a non-polar solvent. Weird. Wow, that's clever. That it can readily attack a nucleophile. So if you take potassium fluoride in benzene and with 18 crown 6, where's my marker here? 18 crown 6, you can actually get a nucleophilic attack. Bam. Right there. 92%. Fantastic. Okay? So, smaller crown ethers bind smaller cations, of course. Lithium and sodium go in 12 and 15, respectively. Please go to conceptual checkpoint 14.4 and practice that. And that's it. That's it for crown ethers. I promised I'd be fast.